Hello, hi, a very good morning to all of you. So now we are back with our new topic as we are discussing in previous lectures about the structure of atom. We have already discussed about the discovery of electron and proton. So students, today we are on our new topic, that is discovery of neutron. So our next topic is discovery of neutron. We have electrons that are completely negatively charged particles, or we may say that these are the negative corpuscles of energy. On the other hand, we have some particles, that is protons, and these are completely positively charged particles. So now we are on our topic neutrons. It means they are neutral particles. They will not carry positive charge or they will not carry any negative charge. So discovery of neutron will be done by Chadwick in 1932. Neutron particles are discovered by Chadwick in 1932 after the discovery of electron and proton. So it means neutron are the neutral particles. They are not going to carry any of the charge. Neutrons are neutral particles. Here neutral means they neither carry a positive charge nor they will carry any negative charge. So here neutral means neither they are positive nor negative. It means they are not going to carry any charge among them. Now our next point is the mass of neutron is approximately equal to 1.675 into 10 raised to the power minus 24 gram, or it may be considered as a 1 AMU, that is 1 atomic mass unit. So it is the approximate mass of neutron after electron and proton. Now we can write the general chemical equation for these type of particles. We will write general equation for these type of particles. We know that beryllium is having a atomic number 4, having a mass of 9. It can be reacted as helium having atomic number 2, atomic mass 4. What we will get in the product side? We will get carbon 12. We will get 6C12 and 01N. So beryllium is having an atomic mass of 4, 9, atomic number 4. It is reacted with a helium, that is atomic number 2, atomic mass 4. In the product side, what actually we obtain? 4 plus 2, it will give the 6 carbon atoms, and 9 plus 4 is 13. So carbon is having a mass of 12 and one mass is distributed over this particle, and this particle 01N, here we are getting these are actually the neutrons. So it means neutrons are the neutral particles having a charge 0 on them and having a mass of approximately 1. So it is all about the discovery of neutrons. There is no such discovery as that we have considered the electric discharge tube in case of protons and electrons. So it is discovered by the help of the following chemical reaction. If someone wants to copy it, please copy it now. So now students, we are on the 4th category of our subatomic particles, and these are called mesons or pions. So after electron, proton and neutron, we have 4 type of particle which have not been in so much detail until now, but these particles are called mesons or pions. Mesons are divided into 3 categories. First is pi mesons, second is mu mesons, and third is neutral mesons. So these are the 3 category of mesons: pi, mu and neutral. Pi mesons are denoted by pi, mu mesons can be denoted by mu, and neutral mesons can be denoted as pi 0. It means they do not carry any charge on them. So pi mesons are called pions or mesons, and these particles are discovered by the scientist named Yukawa. These particles are discovered by a scientist named Yukawa. These particles do not have in so much detail with us, but it can be elaborated into 3 categories, that is pi mesons, mu mesons and neutral mesons. Neutral mesons are indicated by pi over subscript 0. These are basically discovered by Yukawa. And what are the conditions or application of these type of particles? These particles tells us about the stability of an atom or nucleus. These particles tells us about stability of nucleus. So students, we have discussed 4 category of subatomic particles. First one is electron, second one is proton, third we have discovered neutron, and the last subatomic particles are mesons or pions. So it is all about the discovery of particles. Now we will going to discuss about our subatomic models one by one. So in this series we have many models. So our next topic is atomic models. So we have 3 atomic models after Dalton's atomic theory, that is Thomson's atomic model, second one is Rutherford's atomic model, and the third one is Bohr's atomic model. So students, we have 3 models based on the atom, that which scientists say about what are the characteristics of the particular atom. So in this category, first we have Thomson's atomic model, second Rutherford's atomic model, and third is Bohr's atomic model. We have 3 models over here because there will be some merits and some demerits of a particular model which can be sorted by the other scientists and other co-workers. So we will discuss in details about the 3 atomic models. So we will going to discuss about our first model, that is Thomson's atomic model. So now we will discuss our models one by one. So in this category, we have our first model, that is known as Thomson's atomic model. Sir J.J. Thomson discovered much points about electron, but these points do not have any experimental discussion or experimental proof. So our first model is Thomson's atomic model, and we will discuss about the Thomson's atomic theory. So here we are discussing our first model, that is Thomson's atomic model. So students, have you seen a watermelon sometime? Have you observed the watermelon is a red flesh, having a red fleshy part in most of the quantity, and the small seeds are embedded in it. So the Thomson's atomic model is compared with a watermelon, and sometimes it may be known as plum pudding model or plum resin model. What we can see in the pudding, we have some part that is of the icy and chocolatey parts, and some choco chips like substance are embedded in it. It means the fleshy part that contains larger amount of quantity is considered as a positive charge, and the seeds or choco chips here can be considered as a electrons embedded in it. So firstly, what we see in the Thomson's atomic model, Thompson said that an electron is a spherical surface having a sphere of positive charge and electrons embedded in it. The most of the part covered here, that is of the blue color, is a positive charge, and what we see, the negative charge is continuously embedded in this electron. So what is the conclusion of the first point of the Thomson's atomic model? It is given by J.J. Thomson. Second point is, it is called plum pudding model. Sometimes Thomson's atomic model is also known as plum raisin model. So it consists of the positive charge that will cover the entire surface of the atom, and we see here electrons are embedded in the surface. Now Thomson's atomic model is basically compared with plum pudding model. What actually we see here is, in the plum pudding model, the chocolate will occupy a larger quantity of the mass, and sometimes we can say that choco chips are embedded on it. So the most chocolatey part that is covered in larger quantity is considered as a positive spheres, and the choco chips embedded here can be considered as a negative part. So next point regarding the Thomson's atomic model will be, it consists of positive charge sphere in which negative charge is embedded. So here positive charge is distributed over the entire surface, and we see that the negative charge is embedded on that positive charge surface. So Thomson's atomic model is firstly compared with watermelon. What we see here is, we can see this is a positive sphere of red fleshy part. So this red fleshy part is considered as a positive, and we can say, see here, the black seeds are embedded in it. Here these black seeds are considered as the electrons embedded on the positive sphere. So Thomson's atomic model is firstly compared with watermelon, and then it is compared with plum pudding model. So sometimes it is known as plum pudding model or resin model. So it is all about the Thomson's atomic model. So Thomson's atomic model give us some points about the stability of the nucleus. It means the amount of positive charge will be equal to the amount of negative charge. So students, we can write here the merits of Thomson's atomic model. What are the merits of Thomson's atomic model? The Thomson's atomic model tells us about the stability of an atom. First point, it tells us about stability of atom. Stability of atom means the amount of positive charge in a particular sphere will be equal to amount of negative charge. Second point about the Thomson's atomic model is it tells us about formation of ions and ionic compounds. So, Thomson's model tell us about the formation of ions and ionic compounds. It means after checking the stability of the nucleus, that is how much electron and proton it will consist, we can form the ions and ionic compounds. So, here are the two basic merits of the Thomson's atomic model. But in Thomson's atomic model, there are some drawbacks which was rejected by the co-workers and the co-scientists, and after this the Rutherford's gold foil experiment have been done and he gave the certain points regarding the atomic theory of a model. So what are the drawbacks of Thomson's atomic model? We will discuss now. Now we are on our second topic, that is demerits of Thomson's atomic model. So, now we will discuss the demerits of Thomson's atomic model. Thomson only gave the model and compare it with the watermelon and the plum pudding, but this method do not have any experimental proof. So, first drawback of the Thomson's atomic model is it does not give experimental proof. Thomson only gave the atomic model and say that it consists of a positive charge sphere, that is, we have considered it with watermelon as it is a fleshy part that is of the red color and electrons are embedded in it. So this model does not give any experimental proof. Second point, it does not tell us about number of electrons and protons and their position. Thomson's atomic model would not be able to explain about the location of electron and proton. So, in the sphere of this, we cannot centralize where the proton is situated and where the electron is situated. So, he tell only that negative charge is embedded in this positive charge sphere. So, these are the drawback of Thomson's atomic model which can be overcome by the Rutherford, and the next model proposed by the Rutherford is known as Rutherford's atomic model. So, students, now we will discuss about the Rutherford's atomic model. So, students, now our second model after Thomson's atomic model is Rutherford's atomic model. So now we will discuss about the Rutherford's atomic model. So, before discussing the Rutherford's atomic model, we will firstly learn about the Rutherford's gold foil experiment. So, what actually the gold foil experiment is. So, in Rutherford's gold foil experiment, firstly he has taken the alpha particles, and the alpha particles are emitted from a source like polonium, and these are kept in a lead box. So, what we are seeing here is Ernest Rutherford performed the gold foil experiment. He has taken a gold foil having a very thin dimensions, that is of the 100 nanometer or 10 raised to the power minus 8 centimeter thick. What actually he has done? He has taken the source of alpha particle over here. This radioactive source is embedded or enclosed in a lead shield. So, polonium is enclosed in this lead box and the beam of alpha particles is allowed to pass through the screen. Now, he has taken a gold foil. The gold foil has a thickness of about 100 nanometer. Then, he has taken a screen, and screen is coated with a material called zinc sulfide. So, the effect on the screen can be easily observed. We have taken a microscope for observing the deflections from the beam. So, here it is enclosed in a lead box and a lead slit has been taken with a small hole on it, so the alpha particles can easily strike the surface. So what we have observed in this experiment here is some of the alpha particles can easily pass through the screen. Some of the alpha particles will suffer a small deflections, that is on the point CBA here, and some of the alpha particles were bounced back at an angle of 180 degree. So, what gold foil experiment has done? First, we have taken a lead box. In this lead box, we have a source of alpha particle. The source of alpha particle may be any radioactive particle or polonium. So firstly, we have taken a lead box, and in that lead box we have a source of alpha particle. Either it may be polonium or it may be any source of radioactive particle. Now what we have taken here is, we have taken a thin gold foil. Thin gold foil having a dimensions of 100 nanometer, or it is 10 raised to the power minus 8 centimeter thick. So, gold foil is placed over here. Now, we have taken a screen for observing the activity of alpha particles, and the screen is basically coated with a material, and the material is actually the zinc sulfide. Now, what we have taken? We have taken a screen, and this screen is coated with zinc sulfide. So students, here are the basic contents of the alpha scattering experiment. We have taken a lead box. After that lead box, we have taken a lead slit which is having a fine hole for the emission of alpha particles. In that lead slit, we have a fine hole so that the alpha particles can be directly observed on the screen. We have a thin gold foil of dimensions 100 nanometer. We have taken a screen, and the screen is basically coated with a material called zinc sulfide, so the deflections can be easily seen on the screen. Now, we have transmitted the alpha particles from this lead box, and we have observed the three activities in this box, that is at the particle A, at particle B, and at particle C. So what actually we have observed, that most of the alpha particle, about 90.9% particles, can be easily passed through this screen, which can be observed as a fluorescence on the screen at a point A here. So what are the observations of the Rutherford's gold foil experiment? What he observed from this experiment, first point of the observation is most of the alpha particles can be easily passed through the screen. It means about 90.9% particles can undeflected and pass straight through gold foil. It means the particles at point A will not suffer any deflection and they are easily passed through the gold screen. Now, what we have seen, that at the point B, some of the alpha particles are scattered at some angle and suffer a small amount of deflection over here. So, the second point of observation is some particles deflected at small angles. So particles deflected at small angles, we have seen here, these particles deflected at small angle can be observed at point B in the diagram. Now what he has observed, some of the alpha particles return back to their original path with the angle of 180 degree. It means these particles have been bounced back. So some particles, approximately 1 in 20,000, 1 in 20,000 bounced back. So these are the observations of the gold foil experiment, that most of the alpha particles will remain undeflected. Some of the alpha particles are deflected at small angles, and particles about 1 in 20,000 are bounced back. It means they are returned to their original position at an angle of 180 degree. So this is all about the Rutherford's gold foil experiment and the observations he has made. So we can understand it with the help of the simple diagram. So what we are looking here is, this is a gold foil and having a gold atoms. These will have a nucleus at the center. See, what actually happens here is, most of the alpha particles remains undeflected and can easily pass through the gold foil. So in this diagram, we can say that these are undeflected particles. Secondly, we see that few alpha particles will deflect at certain angle. Look at here, here is point B and point B. So these are particles showing deflection. Now look at the point C. What we have observed here, some of the alpha particles will bounce back and cover an angle of 180 degree to return to their original position. So what we are seeing here is, some of the alpha particles are bouncing back, and this is point C, and we can say that these particles are bounced back, and the particles which are bounced back are only 1 in 20,000. It means a very little particle have a tendency to bounce back from here. So it is all about the Rutherford's gold foil experiment. From this gold foil experiment, Rutherford gives some conclusions about the atomic model. So now we will discuss about the Rutherford's atomic model. This is considered as a gold foil atom. In the center, we have considered as a nucleus. Now, what we see here is most of the alpha particles can be easily passed through screen. Few of the alpha particles will deflect at certain angle. And few of the alpha particles will bounce back from their original position. So what we are seeing here, these are the particles which remain undeflected. So these are the particles which remain undeflected. The purple particles I have shown here is the particles showing some deflection. And the blue color particles we have seen here, they are bounced back from their original position. So these are the particles which are bounced back. So it is all about the experimental setup from the Rutherford gold foil experiments. So for the atomic model, Rutherford drew some conclusions from this experiment. Firstly, most of the alpha particles remains undeflected and pass through the screen. It means most of the space in an atom is empty. So what are the conclusions? Conclusions he has made. First, most of space in an atom is empty. It means the particles which show undeflection, it means maximum undeflection, proves that most of the atom is empty. Now we see that some of the alpha particles are deflected at certain angle. It means if some particles are deflected at certain angle, it consists of some amount of positive charge. First point is most of the space in an atom is empty. Second point is it consists of some amount of positive charge. Now the third point about the Rutherford's experimental setup is that the few of the alpha particles are bounced back. It means they are returned to the angle of 180 degree. It means the part of the positive sphere is very small. It means third point is part of positive charge is very small. So from these three observations of the Rutherford gold foil experiment, he has made the three conclusions about the atomic model. So first point is most of the part of the atom is empty. So it consists of some amount of positive charge, and third point of conclusion is the amount of positive charge will be a very small. So these are the conclusions from Rutherford gold foil experiment. So after the conclusions, Rutherford gave his atomic theory, and what are the basic points of atomic theory we will discuss now. Now we have some of the points regarding Rutherford's atomic theory. So first point here is most of space in an atom is empty. Second point regarding this is atom consists of small positive charge which is located at the center. Third point of the atomic theory is volume of nucleus is small as compared to volume of atom because the nucleus is having a small part. So, these are the 3 points of the Rutherford's atomic theory. It means most of the space in an atom is empty. It consists of the small positive charge which is centralized at the center and it consists of the positive charge. Next point Rutherford tell us about the atomic model is number of protons and electrons are same. So atom is neutral. So these are the basic points of Rutherford's atomic theory which cannot be proved by the Sir J.J. Thomson, but Rutherford's atomic theory also has a certain drawback which are overcome by Niels Bohr. Rutherford firstly said that atom has a large space empty in it. In that empty space we have a positive charge, that is nucleus, which is centralized at the center, and the remaining part is covered with the electrons, and electrons are revolving in a particular orbit. Volume of the nucleus which is at the center is very small as compared to the entire part of the atom. So these are the some of the concluded points about the Rutherford's atomic theory. Now the drawbacks of the Rutherford's atomic theory and about the Niels Bohr's model of the atom we will discuss in our next class. This lecture is over for today. Thank you so much and have a nice day.